Thank you for the kind invitation and introduction, and thank you for the opportunity not only to have this lecture, but to be able to work at this very creative environment. Yesterday in the morning, basically the same time as you started today, I gave a lecture at elementary school for 5 classes, and I'm enjoying the quietness of this audience. But hopefully afterwards we'll have a very fruitful discussion. So this will be mostly an introduction into something what is a very interesting world, which may or may not exist, as a little teaser. And it probably warrants a nice discussion of very wisdomful people as are gathered in this room. So let's go ahead. The story so far is this. I said it before, I'll try to say it differently. The story of physics so far is a story of merging different theories together. So back in the days, we had electricity and we had magnetism, and then Maxwell came and figured out, well, they basically fit into a set of 4 equations within a single framework. Then, nearly by accident, he discovered also optics being part of the same picture, and another branch basically joined the other. So for a moment, we kept rediscovering theories that just very naturally fit into same set of theories or into a single framework. And now we have 2 final sets. One is the quantum mechanics or quantum theory in general, and the other is the general theory of relativity. Now, the obvious punchline of this is maybe these are still about to join somewhere, forming a single theory. But I want to talk a bit about mathematics and how mathematics have been changing along this direction. So when we first discovered mathematics, they were motivated by our daily lives. Like the first application of Pythagorean theorem was taxes. So everything mathematics studied was something you can apply to your everyday world. Then we moved down into more general frameworks, and now if you want to explain Maxwell equations to students, you first have to teach them how to solve differential equations and so on. So yes, branches are joining together into more general frameworks, but mathematics are becoming different and maybe more separated from our everyday lives. So explaining gravity in terms of Newton's law of gravity is basically manageable at elementary school level. Now explaining general relativity requires some mathematics. Now we are trying to move down here, and the obvious expectations is we should be expecting some sort of new kind of mathematics to be involved. Maybe yes, maybe not, but some things you will see in a couple of minutes will be probably new to you. They might look unnatural, but this is what is happening when you are trying to climb down the trees. We are encountering new and new math. And now, when we are trying to move maybe the last step and connect to, not sure if I can call this branch or not, but connect those 2 branches together, maybe we need totally new kind of mathematics. Maybe yes, maybe not. We'll see. So this is the story so far. In 100 years, let me round it down, 100 years to get to this point. Very quickly after discovering quantum mechanics, people made some efforts, and then they kept making efforts until today. And at this moment, we have some theories that are both quantum and continuum gravity, but we are unhappy with them for different reasons. So the unfinished tale looks maybe like this, and in this presentation, we won't be able to get to the roots of the problem, to see if those 2 theories are actually part of one single theory, which would be maybe even a boring answer. If you try to join general relativity with quantum mechanics, and it just works, it would be a very boring answer. So far, every time we try to join something, new mathematics, new phenomena, new everything appeared. So maybe we should be thankful that this task seems to be very difficult, because it's promising huge rewards. Like maybe actually obtaining different point of view on understanding what physics is. So this is the difficult part. Now, there are many candidate theories for the quantum gravity and quantum space. And it's a little bit tricky because you have way too many different theories like quantum string theory, quantum loop gravity, different theories of dynamic or triangularization and so on. And it isn't clear which one of them is correct. Some people will say it's the string theory, some people are hoping for the loop quantum gravity and so on. So I'm, as a young scientist, arbitraging my opportunities and picking a phenomenon that is common across various theories. So many theories of quantum gravity share a common feature, and the common feature is a quantum nature of space. That means the space is composed of something. How come we haven't noticed so far? The explanation is we haven't been zooming well enough. So during preparation of every lecture, most of my time is spent doing something completely unproductive. So for this one, I was searching the Google Earth for most homogeneous part of the globe, which is this. Can you guess which part of the Earth is this?
Sahara.
Yes, it's Sahara Desert. So you can keep zooming. I have blurred this one to make it more difficult, but you can see there is something appearing as you are zooming in. So the same thing as seen from high altitudes looks like a perfectly smooth and homogeneous space. And as you are zooming in, then you start noticing some kind of structures. This is from a different part of Sahara Desert, but you get the idea. So the question is, where should we be looking for this kind of effects? Like, how many times do we have to zoom in to see the structure of space? Not sand dunes, that would be very surprising, but something. Currently, we see the space is something very continuous, homogeneous, nothing going on there. So how many times do we have to zoom in to see something? Actually, this is interesting because 50 years ago, zooming was like this, and now we zoom on screens like this. So I'm not zooming with a telescope, I'm zooming on a screen into empty space. And this is as Juraj said it, the job security slide. Because the effects become prominent, we assume on a scale that is very, very small, lengthwise, and very, very large energy-wise. So these energies are way larger than anything achievable particle colliders. And these distances are way too small than anything that we can resolve using a microscope of any kind. These were derived first by Planck, but there were previous efforts before Planck, which is very difficult because Planck's constant is one of the 3 ingredients. So if you are trying to compute Planck units without Planck's constant, you won't be able to get the correct result. Someone's right before it, Planck did it. So basically he asked the question, these 3 constants are important in nature. This is the speed of light, gravitational constant, and this is the Planck's constant, basically telling you at which scale you cannot ignore effects of quantum mechanics. This is telling you at what velocities you cannot ignore the effects of special relativity, and this at what masses you cannot ignore the curvature of space. So he asked the question, can I combine this into something different? And obviously you can. There are different mixtures. One of them is called the Planck length, which is this very small number. The other one is the Planck's energy, which is this very large number. And there is a whole set of Planck units. You only need to have those 2 in mind. So again, zooming into the Earth, if we zoom, starting from the orbit, this is probably, I don't know, GPS orbit, you zoom into Earth, and you are zooming for a long while, and now you see the nucleus. The bad news is if you are doing this, you are still halfway to the Planck length scale. And this is the tricky part. In a century, we knew Earth before a century, but within last century, we were able to move from those scales to here. It was a great effort. And maybe somebody can be very hopeful, like we can keep doing the same thing for 3 more centuries, and every century we will move 5 orders of magnitude, and then in, 20? So in 4 centuries, we'll see Planck's length. Maybe, yes, I'm not such a techno-optimist for this. We should be looking for something different, not hoping to see the effects of quantum space in particle colliders. There might be some clues, as Juraj suggested, but building even larger particle collider wouldn't work for finding effects of quantum space. You can calculate what size of accelerator would you need for that, and the size is, rough estimate is the solar system. And you would have to be very good in writing applications for funding to build something like this, and such a feature hasn't been done so far. So how to do this without this? Juraj said that, well, direct evidence is impossible within the next century. And we are working on similar topics, so I don't want to sound like a copy of him, so I'll contradict him at some places, and this is one of them. One can argue, at least philosophically, that directly you don't see anything. Everything is being measured either by some kind of instrument or your eyes or something. And then your brain or your scientific center or something is trying to piece together the pieces of evidence to form some kind of representation of the world within some internal framework. This being a scientific theory, this being your mental representation of reality, something like this. So everything we see is actually indirect. And if everything we see is indirect so far, I will be happy with indirect evidence of quantum space because it's as good as anything else we've done so far. So how to think about this? As I said, maybe we are not waiting for next Einstein, but we are waiting for next Riemann, which basically prefer the mathematical framework for Einstein to develop his theory of relativity. Now maybe we are waiting for someone to define new mathematical structures. This hasn't been done so far, so we are using what we know from previous studies of the universe. So in quantum mechanics, we learned that you have operators that are describing physical quantities such as velocity, position, angular momentum, and so on. If you want to measure something, then it depends on what is the order of measurements. And if you first measure the position and then velocity and the other way around, you'll get a different result. Now we want to describe a space that has some kind of structure, which means if you first measure this position of a particle and that position of a particle, you might be expecting a different result. So we are borrowing the tools from quantum mechanics and invoking them onto the space itself. A new constant appears that has dimension of length, which we assume to be the Planck's constant because nature is telling us or suggesting us that something is happening on this length scale. And we are expecting something to be happening with the space, so why not to expect at least those two parameters to be the same or of the same order? So we are basically using the tools, for example, of quantum mechanics, quantum field theory, and trying to modify them to include quantum nature of space as well. So basically, you can view this as a modification of quantum mechanics with different regards. This is the nice part. We sort of at least know what to do to get some predictions. Now, the tricky part is this. You should be scared from seeing this because this is the thing that makes everything really difficult to measure. Every result we get is of this form. So you have some prediction for the mean, velocity of a particle. You get a classical result, which is something, and then you have some corrections. And these corrections are proportional to the energy of, for example, the particle divided by the Planck's energy to some power. And as I said before, these might be the largest energy producible in the universe. And this is the energy you can produce as a tiny little human. So it's very, very difficult to make this number not very, very small and not to make this correction indistinguishable from zero. So this is the tricky part. We basically know what to do. It's not maybe mathematically super consistent in every aspect, but I don't care that much. I'm a physicist. So if it would be working, we would figure out the math later. So we sort of know what to do. But now we would like experimentalists to be able to see this. And we show them what we want to see, what is the precision, and they say, no way, because this is just way too small. This is 10 orders below anything we can see right now. So the ball is back on our side. Theorists should find some indirect measurements or something that has sort of leverage, which can make those small effects actually large or at least noticeable. Okay, no. So now I will discuss 3 different topics from the phenomenology of quantum space. These are not covering the whole field of quantum space phenomenology. This is just something I have been involved in or have been involved in or want to be in next year. So this is something I find interesting. There are many other things. I don't want to claim that this is everything people figure out so far. The first idea is related to small black holes. Black holes are usually not small from a human comparison. They are small from astrophysical comparison because everything is millions and billions of kilometers. And usually black holes are like 3 to 4 kilometers or 10 kilometers, very small. But when I say small black hole, I actually mean a black hole that is size of the Planck's scale, maybe even, and the mass of a speck of dust. So very small black holes, maybe slightly larger, but this is the smallness I'm talking about. How to find such black holes? Usually when you want to form a black hole, you take mass and you keep squeezing it until it forms a singularity. Singularity is a point of infinite mass, and now we are trying to investigate the features of theory which has quantum structure of space, which means there shouldn't be an exact point. Maybe you can narrow it down to the Planck length, but not any further. So how would black holes behave if we prevented them from forming perfect singularity, and the singularity would be stopped at some distance and mass scales? So what you can do is you can take something that looks like a delta function. If this is a very small number, then this exponential is decaying very, very quickly. So it's like from something to 0 within a couple of Planck lengths. So it's looking like a delta function, but it's not completely a delta function. You take this, you plug this into Einstein field equations, and you solve for them. You find the descriptions of a black hole with regular mass, which are usually called regular black holes, and you study their properties. And one of the most important properties is their temperature. The temperature I'm referring to is the temperature of Hawking radiation, which we can see in the ordinary case goes like this. As the black hole is getting smaller and smaller and smaller, the Hawking temperature just goes to infinity. An important aspect of every theory of quantum space is not only you are removing very short distances, but dual to them very large energies. So the naive expectations is that if you have a black holes that is sensitive to the quantum nature of space, not only singularities should be avoided, but infinite temperatures should be avoided as well. So you take this type of blurred singularity, plug it into Einstein field equations, solve for them, find the Hawking radiation profile, and it looks like this. Instead of it's heating up, and then instead of going to infinity, it just freezes to 0. First, we studied this for a certain model of 3-dimensional quantum space, and then with one of my students, we tried to generalize this result as much as possible, and under very general assumptions, this holds. If you take a regular matter density, infinite temperatures are avoided, and instead the object freezes to 0. So under very broad assumptions, we have proved this. And it's very interesting. Here I got asked a question, what about the rest of the universe? So here I can add my 2 cents. What do we know about the universe so far? Well, it's mostly something we don't know. We know stars, gases, everything in between which we can observe with telescopes, hot plasma, etc. Then things which are difficult to observe, but we know they are there and sometimes we get to measure them, for example, neutrinos. Then there is stuff that we are nearly sure is not interacting in ordinary ways, but gravity, which we call the dark matter, which is behaving as matter, and that's it. We don't know anything else. We know some temperature profiles, etc. But it might be a particle which is interacting very little. It might be something completely different. It might be some artifacts of different descriptions of gravity. So people are trying to figure out what dark matter could be. And then there is dark energy, which we know basically close to nothing. We know that it's a driving force of the acceleration of the universe. There are some suggestions what would the energy profile of dark energy might look like to drive the inflation and then stop the inflation and so on. But there are some ideas how to formulate a good theory of dark energy. But I would be hoping for this within the next 100 years and not so much for this. But maybe I'm overly pessimistic, and maybe this will be done in 3 years and this in 10 would be surprising. So, but what from the perspective of quantum space I can say about those two? Close to nothing about this one and something about this one, something about dark matter. Because what happens to small black holes is their mass tends to Planck mass, their size tends to Planck's length, and their temperature goes to 0. Planck's mass is small compared to me, but it's way larger than any fundamental particle. Really, this is the mass of a single grain of dust. The size is basically the cross surface, the cross ratio is on the order of Planck's area, which is 10 to the minus 70 meters squared. It's impossible to hit a microscopic black hole, but it's still quite massive. So it sort of looks like a good dark matter candidate. I have calculated that for them to make up the observed dark matter density, you would need a single microscopic black hole per volume of 1,000 kilometers, if I recall correctly. So just take those microscopic black holes, maybe as a leftover of universe formation, and just sprinkle them across the universe, and they would sort of work like dark energy. Well, not so quickly, because during the process of evaporation, most of the time, the mass of the black hole, which is Hawking radiating, is way larger than the momentum of the quanta of radiation it is emitting in every direction. But during the final moment of evaporation, the momentum of the black hole and the radiated particles move towards to each other, and it basically looks like the small black hole is doing something like a Brownian motion, just radiating into random directions. And after this process, it's left over with a speed which for different models is of the order of 10% of speed of light. So this is something we should be trained as physicists. If there is a theory you like, but you find something that is contradicting it, you should be publishing it as well. So I like the theory of dark matter being made of small black holes, but I found that this should be contradicting the low temperature of dark matter, which we know is at most warm, not hot. So I published the findings. And there a group from United States wrote that, well, what about the expansion of the universe? So then I figured out, okay, expansion of the universe can slow them down again. And actually together we produce like the estimate, what is the last moment when microscopic black holes could have been formed. And the result ended up being very close to the end of inflation era as computed by other cosmological models. So for me, still, this is a good model of dark matter. Leftover inhomogeneities being gravitationally clumped together during the first 10 to the minus 28 seconds after the Big Bang. Okay, now for something completely different, an important aspect of any theory of quantum space and some adjacent theories as well is modified dispersion law, which is basically the relation between the velocity and energy is different from what you might expect. I just took this plot from a paper of Amelino Camelia and this equation from our paper. And basically the idea is this: depending on the energy, even the speed of light can be different from the speed of light. I think actually calling it the speed of light is a misnomer. It's just historical accident that the first thing that is massless and we have observed it to move at this speed was light. So we call it the speed of light, but it should be thought of as some kind of maximal velocity in our universe and maximal speed in our universe. And even light can move slower, which we know if it's moving through water, light is slowed down. And here we can claim that actually quantum nature of space can slow down light, and it's sensitive to different wavelengths. So the shorter the wavelength, the more sensitive it is to the underlying structure of space. So the prediction is we should expect something like this. And these are the observations. So this is the energy of observed particles, and these are the time delays. So the claim is the more energetic particle you observe, the larger gap between some kind of initial gamma ray burst there is, you can expect. How can we see them? Well, basically these are gamma ray bursts, which are both very luminous and very energetic. Very energetic means this term isn't as small as it might be, and luminous means we can see them across the universe. So it means we can look at the ray that has been traveling for 10 billion years and hoping to see a small gap, like short wavelength first, then medium, then long wavelengths, or the other way around, depending on the modification of this relation. And this result looks very promising, like it's nearly sitting on a line. And what are those two type of points? This is for gamma ray photons, and this is for gamma neutrinos, so very large energetic neutrinos, and they seem to be sitting on the same line. I would advise huge caution against this plot, because I think the data I don't want to suggest they have been cherry-picked, but sort of. Like they picked very carefully which data to include, which to not, but at least as a suggestive evidence that this is what we might be hoping for with better telescopes that have been launched so far. Actually, one of them last week or 2 weeks ago. Then there are some other interesting physics. So for example, sometimes photon hits a photon, and when one of them is very energetic and the other is low energetic, they can produce electron-positron pair. So this means that since the universe is full of low energy photons from cosmic microwave background, from distant galaxies and so on, very high energy photons should be prevented from traveling across the space. We have observed very, very energetic photons in last years, many of them. So it means that maybe there is something preventing them from hitting the low energy photons. And the same vacuum dispersion law can be used to basically derive the modification of a mass of a particle produced in this collision. So this will be the prediction of standard physics, and then there is some correction, which is small because it's divided by Planck's energy, but it's also divided by the energy of the background photon. So if this one is small enough, it can cancel this effect and actually make an observable predictions. Unfortunately, there are other excuses. How could those particles overcome those speed limits? But again, suggestive evidence. Now there is a question about extra spatial dimensions. So I just prepared this slide in case you want to ask about them again. We can say something about the number and the size of extra dimensions within this context. We did this and basically disproved any number of dimensions, extra spatial dimensions, considerably larger than the Planck's length. And this is about the future. This is something what I would like to spend more time on, is understanding the effects of quantum space on the creation of the universe. Because phenomenology is about something that happens or is happening, and the thing that the universe exists is one data point, which is just one, but it's very robust, important, and so on. So I'm trying to figure out if there are some theories of quantum space or some theories of something that contains quantum space as its feature that can describe the earliest moments of the universe. There are some theories. Harold here can probably tell you more about it sometimes in the future. There are matrix cosmologies, string cosmologies, different models coming from the M theory predicting some kind of behavior that looks like a Big Bang or two Big Bangs, and then some sort of early cosmology evolution. So seeing how quantum space fits into this picture can be very, very interesting and illuminating. So the thing we are trying to see if the space is composed of tiny little patches. And probably the way how to do this is not to hope for one single overwhelming piece of evidence, but to make a mosaic, like study the threshold anomaly, vacuum dispersion, small black holes as a part of dark matter, and so on. And together, gluing those little pieces of evidence, maybe we will persuade ourselves that space indeed is quantum on its most fundamental level. Thank you for your attention.